The agenda for this video is follows. And we're going to look at the two sample t-test with equal variances between the two populations and equal n's per group. We're going to set up the hypothesis. We're going to look at the distribution of the test statistic under the null and alternative hypothesis, and then we're going to illustrate these concepts in R. So to set up the test, we assume our data follow a normal distribution with some mean mu1 and variance sigma squared. We have another population of data, sample size n, same as this n, follows a normal distribution with mu2 and the same variance as the first population. We're going to test, are the mu's equal or are they not equal? Our test statistic, t statistic, is going to be the difference of the sample means divided by the pooled standard deviation divided by the square root of 2 times n minus 1. And these are our sample statistics with the significance level at alpha. Now, under the null hypothesis, the test statistic follows a central t distribution with 2 times n minus 1 degrees of freedom. And under the null hypothesis, meaning assume that the means are different, we follow a non-central t distribution with 2 times n minus 1 degrees of freedom, and non-centrality parameter this, the square root of n over 2 times the difference of the true means, mu1 minus mu2, divided by the standard deviation. Okay, I'm on R on an Ubuntu Linux-based machine, and we're going to look at the two sample t-test with equal variance and equal n per group. We're going to calculate power and sample size. Now, to illustrate, we're just going to pick an alpha of 0.05 and an n of 20. And n is 20 in each group, so a total sample size of 40. We're going to create some X data to plot, and then we're going to plot the t-test. So over here is the two sample t-test, equal variance, equal n, two-tailed. So we need to set up critical regions here such that this area in the tail is alpha over 2 and this area is in alpha over 2 since it's a two-tailed test. So we'll shade in both regions, and when we calculate the test statistic falls in either rejection region, the red shaded area, we reject the null hypothesis. If it doesn't, then we don't reject the null hypothesis. Okay, but to calculate sample size or power, we have to assume that the alternative is true. And that means we have to pick values in the alternative region. And that means mu1 and mu2 are not equal. And we also need the population standard deviation. So I'm going to sort of just randomly pick values. Mu1 is 3, mu2 is 2, and sigma is 4. And store those in these values, m1, m2, and sig. Next, we want to create this non-central t distribution with these parameters. So when mu1 is 3, mu2 is 2, and sigma is 4, we get this non-central t distribution. And to calculate power means what's the probability we fall in the rejection region, assuming that this distribution is true. And so we need to shade in the area under the curve under those rejection regions. And that's what we did. So it's a probability of falling in this area or this area. And so the rejection region is here, but to be under the curve is just a little sliver of area there. Now, to calculate power, R has a function called power.t.test, and you plug in your sample size. We're using 20. Our delta is 3 minus 2. Our sigma was 4, 0.05 alpha level, and we are using we want to calculate power, so we're leaving that null. It's a two-sample test. It's a two-sided test. And I'm going to illustrate what this strict parameter does. I'm going to say false, which is the default in R, and false means it calculates the area under the curve under one side, and that's the side that has the most area. So calculating this, we get a power of 11.7%, and that's the area under this tail only. Now if we look at the same setup, but we're going to say strict equal true, that means it calculates this area and this little sliver here. So let's calculate that. And the power is 12% because this little piece is adding some to the power. So you have to be careful when you use the default setting in R. Now let's calculate this from first principles. Since this is a non-central T distribution, R has a built-in function called PT, which is a cumulative distribution function. And we want to calculate the area in this tail. And to do that, we want to calculate it from this critical region, which is the shaded area. That's how that's calculated. And then the non-centrality parameter is here. Oh, this is the degrees of freedom. This is a non-centrality parameter, and we want the right tail. That's what the lower tail faults mean. So let's calculate that. And notice it is 11.7%. And so let's open this window, and it's exactly what R calculated. So it calculated this area here. So let's go back to here and calculate the lower tail, which is this. So it's really small. It's not a big area, but it's non-zero. And so let's add those two, and we get our 12%, which is exactly what the power.t.test calculated when we said strict equal true. So now let's calculate the needed sample size in this setting. So here we're going to use power.t.test again and leave the n null or empty. And remember, this is per group, and we're going to use the same delta, 3 minus 2, standard deviation of 4, sigma 0.05, power 0.8, 2 sample, 2-sided, and we're going to look at the strict false and the strict true again and see what that does. So here is the strict false, and it says we need roughly 253 subjects to achieve at least 80% power. Now let's look at the strict equal true, and it also comes up with 253 subjects per group to have at least 80% power. And the reason that they're the same is when you increase n, the non-centrality parameter increases, and this distribution floats to the right, or it shifts to the right, and so this area becomes more and more over this region, and then the area under this curve in this is essentially zero, and so that's why it produces similar results. But I still like to have the strict equal true. So now let's calculate the power using the first principles. So we're going to put in 253 subjects. We're going to calculate the area to the right, and we get 80%. And that's what the t-test, the power.t.test indicated we'd get. But what's the area in the left tail with 253 subjects per arm? And it's a very, very small amount, close to zero, but it's non-zero. So we can calculate the power, and it increases by just a little bit. So that's the end of the illustration. Hope you enjoyed it.